In this video, we're going to extend the ideas that we were talking about before related to the definite integral. We were looking at Riemann sums and figuring out how we could say that the area under the curve estimated by the sum of these rectangles was equal to the integral between two boundary points. The first two items that we're looking at here are definitions. The first one is saying that if we switch the order of the bounds on the integral, going from b to a rather than from a to b, that would be the same as taking the opposite of that integral. Because most of the time we're talking about some point a and moving to some point b. And so we're looking at integration this way. But if we went the other direction, we would be going backwards, and so we would have a negative number to consider. The second one is actually what this picture is written for. It's saying that if we have, if we're going between the exact same points, we have a zero width, so to speak, for that for the base of that rectangle, and so the area in that case is going to be 0. This third one is letting us know that if we have a constant that's being multiplied by a function that we're taking the integral of, we can pull that constant out into the front of the integral and then just work with the function on its own. Let's look at a proof of that using the Riemann sum idea. So we're looking at the integral from a to b of some constant being multiplied by a function. Switching this into the definition that we were using with Riemann sums, we were taking the limit as n goes to infinity, and then summing up the rectangles from 1 to n. The height of each rectangle will be that f of x sub I, and then the base of each rectangle is the delta x. The rules of summation say that we can bring this k out into the front of the summation because it doesn't have the variable n involved in, or the variable I involved in it. So I'll bring that out to the front. And then similarly, the rules for limits say that we can bring that k out into the front because it doesn't have the variable n in it. So I've got k times the limit. I don't want to draw my sigmas correctly today for some reason. And then this part is just the integral from a to b of f of x dx. And we've got that k out in the front. So that's what we wanted to show. That's a fact that'll help us simplify some of the integration that we'll be doing later. Looking at the next slide, we have a couple other ideas that might seem maybe sort of obvious. The first is a sum and difference. The first picture shows the idea of a sum. If I had a function f, it's represented by the blue area there, and I added it to a function g, which is that orange area, taking the area of those two combined is going to be that larger green area down below. So it's saying that we can take the integral of each individual function, and that'll be the same as taking the integral of those two functions added together. The benefit to that is we can, when we start thinking about integrating, we'll think about each individual term on its own, and we can kind of deal with those particular parts of a function individually. Looking at the additivity rule, it's saying that if we are talking about a particular area between two bounds, A and B here, and then we're adding on another area between B and C, that would be the same as just going from A all the way through C. So we're going from A to B for the first integral, B to C for the second, and we could just combine those two together as one integral. And then the third is also something that is kind of obvious from the picture. It's saying that if we have some function f that is greater than some other function g everywhere in a particular interval between a and b, then the integral of f is going to be larger than the integral of g. It kind of makes sense just by looking at the picture. All right, let's do a proof of the additivity property. So we're starting with two functions that are being added together, two different functions. And if we rewrite them in terms of the Riemann sums, we'd have the limit as n goes to infinity f of x sub I plus g of x sub I times delta x. The rules of summation will let us break that into two separate sums. So I'll do that. I'll leave the limit on the outside here. I'm going to distribute this delta x to both of these and then split them into two separate sums at the same time. So I'll have f of x sub I times delta x, and then I'll have a separate summation, g of x sub I times delta x. We can do the same thing with the limit. We can distribute the limit to both of these summations. So I'll do that next. Oops, plus. Okay. And then going back to our definition of the integral, this part here is the integral from a to b of f of x. And then this part here is the integral from a to b of g of x. So this is just showing us that we can split the integral of two functions that are combined into two separate integrals. We're using this idea now, and we're going to use this for a lot of examples going forward, that when we talk about the integral between 2 points of a particular function, that is going to be translated to the area under the curve. The first example is saying that if we're taking a function which is a constant, the integral of that is going to be c times b minus a. Let's draw a picture to think about what that's saying. It's saying that if I have a function which is a constant, let's say it's like here, and then I'm taking the integral between 2 points, a and b, we're talking about this area, right? We're talking about the area that is this rectangle. Well, the way that I would calculate this rectangle, I would take the height, which is c, and then I would take the base, which is b minus a. So it's just saying here that if I take c multiplied by b minus a, that will give me the area of the curve, under the curve between those two values. The second example is what happens if we integrate the function x, which we can see in the picture over here. I did a proof, it's on Canvas, that shows the algebraic way to think about this using Riemann sums. But looking at the graph, if we were to say, think about this area, which is b squared, this whole square there. And then consider this area here, which is a squared. But because I'm looking at the area under the curve, I'm taking half of those. So if I take that larger b squared and I subtract off the a squared, and then I've got half because it's underneath the line y equals x, that's how we're getting this formula here, b squared minus a squared over 2. The third example is what a general formula that we can use if we're integrating x squared. And the proof for that can also be done pretty easily using Riemann sums, similar to the proof that I showed for the x, for the integral of x.